We pointed a telescope into the darkest corner of the universe, down into an abyss where light has been traveling for billions of years. And there, we found something that shouldn't exist. Massive galaxies that scientists called impossible. That the laws of physics screamed, this can't be here. None of our models predicted this. The James Webb Space Telescope found exactly that. And right now, the world of astrophysics is quietly shaking. Because either our models were wrong from the start, or the universe has been hiding a story it never told us. Look, for decades the answer was clear. The Big Bang happened, the universe expanded, cooled down, and sank into darkness. Then, for hundreds of millions of years, nothing happened. Gravity slowly gathered gas clouds together, and the first stars ignited. Galaxies didn't just pop up overnight either. Small pieces smashed into each other and grew over billions of years. So if you looked at the earliest periods of the universe, you'd expect to see tiny, faint, scattered structures. But here's the thing. We didn't have the right tool to see those periods. The Hubble Space Telescope did incredible work for over 30 years, but its mirror was only about 8 feet across, and it mostly worked in visible light. The light coming from the universe's oldest galaxies had been stretched over billions of years by the expansion of space, shifting into the infrared. Hubble couldn't see that light. James Webb was designed specifically for this. Its 21-foot gold-coated mirror can collect 6 times more light than Hubble's. And it's not orbiting Earth. It sits about 1 million miles away, at the L2 point, shielded from the heat of the Sun, Moon, and Earth. A sun shield the size of a tennis court cools it down to nearly negative 400 degrees Fahrenheit. In short, Webb is a machine built from scratch to capture the oldest light in the universe. And when this machine turned its mirrors toward that darkness, when the universe was only 300 to 400 million years old, so young you can't even call it a baby, there were massive galaxies sitting there, as massive as the Milky Way. Think of it this way. You walk into a preschool classroom expecting to see kids, but instead, there are bearded adults in suits sitting at the desks reading newspapers. That's exactly the shock astronomers experienced. They called these galaxies universe breakers, because these things shattered every mathematical equation we had written about how the universe is supposed to work. And it's not just one. Take Jade's jwst 14.0, for example. It's shining just 290 million years after the Big Bang. It has a mass 500 million times that of our Sun and produces roughly 20 new stars per year. It spans 1,600 light-years across. And they detected oxygen in it, which means multiple generations of stars had already been born, lived, and died. That level of chemical maturity, that early on, was in nobody's calculations. Then there's GNZ11, a galaxy that existed when the universe was just 430 million years old. It had been discovered during the Hubble era, but thanks to Webb, we now know it has an active supermassive black hole at its center, weighing 2 million times the mass of our Sun. They even found a cloud of pure helium gas surrounding it. This could be one of the first indirect pieces of evidence of the universe's first stars, known as population 3 stars. And then there's Maisie's galaxy, shining when the universe was only 390 million years old. So this isn't just one weird example. Webb is finding galaxies like these everywhere it looks. Now you might rightfully ask, maybe the telescope is wrong. Maybe there's an error. The scientific community debated this heavily in the early months. But no, the data has been confirmed again and again. Webb measures the age of light using something called redshift. The redshift value of Jade's jwst 14.0 is 14.32. That's the highest value ever measured. So how? How did these massive structures form when there wasn't enough time? The first explanation involves dark matter. This stuff makes up about 27% of the universe, but we can't see it. It's essentially the skeleton of galaxies. Maybe in the early universe, dark matter was working much harder than it does now, pulling matter toward the center like a magnet, growing galaxies far faster than they should have. In other words, gravity was in turbo mode. The second explanation involves stars. These first-generation stars, called population 3, were unlike anything we see today. They were made of nothing but hydrogen and helium because the universe hadn't produced heavier elements yet. Because of that, gas clouds couldn't cool efficiently, and instead of fragmenting into small stars, entire clouds collapsed into single, massive stars. How massive? Computer simulations show they could have been 30 to 300 times the mass of the Sun. Some theories push that number up to 100,000. Hold on a second. 100,000 solar masses in a single star. Their surface temperatures were around 180,000 degrees Fahrenheit, roughly 20 times hotter than our Sun. They radiated enormous amounts of ultraviolet light, but in return, their lifespans were only a few million years. Then they exploded as supernovas and scattered the first heavy elements across the universe. None of them have been directly observed yet, but Webb may have provided indirect evidence through that pure helium cloud around GNZ11. Still, even these massive stars aren't enough to explain the total mass Webb has observed. The third explanation is the craziest one: giant black holes. We always thought it worked like this. Galaxies form first, and then black holes slowly grow at their centers. But the data coming from Webb might be saying the exact opposite. In the standard scenario, black holes grow step by step after massive stars die, swallowing other stars along the way. But that path is way too slow to create supermassive black holes within the first few 100 million years of the universe. There's an alternative model: direct collapse. At the very beginning of the universe, massive gas clouds that couldn't cool down skipped the star phase entirely and collapsed directly into black holes. These seed black holes may have been born with masses between 10,000 and 100,000 times that of the Sun. Then they rapidly swallowed the gas around them and forced galaxies to form in their vicinity. The active black hole in GNZ11 seems to support this scenario. So maybe galaxies didn't create black holes. Maybe black holes created galaxies. You might be thinking, okay, so did the Big Bang Theory collapse? That's exactly what spread across social media. But it's not that simple. We still have very solid evidence that the Big Bang happened. The cosmic microwave background radiation, the expansion rate of the universe, those are still holding up. The Big Bang happened, that's certain. But when it comes to telling the story of what happened afterward, it looks like we skipped a lot or miscalculated. That's the bottom line. And the beautiful part is, James Webb is just getting started. In the coming years, it will try to look even further back, all the way to the moment the first stars were born. Maybe we'll find a period where the laws of physics worked completely differently. NASA, ESA, and other space agencies are currently preparing new programs to solve this cosmology crisis. But honestly, I wouldn't call it a crisis. The places where there are more questions than answers are where science gets the most exciting. You know, while putting this video together, the thing I kept thinking about the most was this. Here we are, inside a 14 billion-year-old universe, on a tiny planet, with our 100-year lifespans, trying to understand the first 300 million years of the universe. And thanks to a telescope, we're actually finding clues that we might be able to understand it. That's enough for me. So what do you think? Is dark matter behind all of this, or is it the giant black holes? See you in the next video. Goodbye.